The objectives of the Weir calibration laboratory experiment are to determine the head-discharge relationship of weirs of different shapes and to compare the experimental results to the corresponding analytical expressions derived. A weir is a barrier placed across flowing bodies of water designed to alter flow characteristics such as increasing or decreasing the water level or to change the direction of the flow. Weirs are used in rivers and they are similar to dams but smaller. There are several different types of weirs which include V-notch, rectangular, broad-crested, sharp-crested, and compound weirs. The head-discharge relationship for each of the weir shapes was derived analytically using the following formula. The weir of the desired shape was attached to the testing apparatus. The point gauge reading of the reference point of the weir was obtained, and we waited 2 to 3 minutes after beginning or changing flow conditions to allow the apparatus to stabilize. For each of the 6 flow conditions, the discharge was measured using a container and stopwatch. The discharge is determined by filling a container with water flowing out of the drain opening. The time elapsed to fill the container was recorded, and the weight of the water was recorded. The discharge could then be calculated since we know the filling time and the accumulated water weight. This measurement was repeated 5 times for each discharge setting, discarding the highest and lowest measurements and averaging the 3 remaining measurements. The point gauge reading of the water surface upstream of the weir for each discharge was obtained. Then, the head over the weir for each discharge was determined by subtracting the point gauge reading of the water surface upstream of the weir from the point gauge reading of the weir reference point. The following table is the data that was directly measured in the laboratory. For the experiment, there were 6 flow settings. 5 measurements were taken, and the largest and smallest values were discarded, and an average was taken of the 3 remaining. The graphs shown are of log Q versus log H for the rectangular and triangular weir. These graphs were used to determine the values for A and N, which is the weir coefficients. A trend line was added to the plotted values on the graph. The value for N is found from the slope of the trend line, and the value of A was found from the inverse log of the y-intercept of the trend line. For the rectangular weir and the triangular weir, the N and the A values are shown below. All necessary data was calculated for the rectangular and triangular weirs and used to plot a graph of discharge versus HN. The accuracy of the following data can be visually analyzed by inspecting the reference of that data to the trend line on the charts. The data does not vary and is close in proximity to that of the trend line. Therefore, the data is reputable and the analysis is accurate. There is 16% error here in reference to the theoretical value for N. In the experiment that was conducted, the dimensions of the weir were small and therefore the values of N and A will both have some degree of error associated with them. The error between the calculated and the theoretical values for A was found to be 23.5%. This number is large, but taking the size of the weirs into consideration and the errors associated with measuring the discharge using a bucket and a stopwatch, the cause of the error is easily identifiable. If the experiment were conducted for a second time with a larger weir in place, the error in A and N as compared to the theoretical value would be less. For the triangular weir, there was a 68% error for N and a 68.5% error for A when comparing the values found during the experiment and the theoretical values. To reduce the error, the experiment could be performed again on a larger scale. Also, there was an error associated in calculating the discharge using a bucket and stopwatch method. Longer time intervals in which the water would have been collected would help to reduce this error.